Доброе утро.
Привет.
Кто-нибудь знает, мы по той ссылке сидим.
Я не знаю. Ты где ее взял?
Я выше в канале нашел. Он кидал.
Мгм. Да, мы по той ссылке сидим, видишь?
Да, отлично. Аким, а можно узнать, вот мы пишем сейчас что-нибудь на листочках, потом берем, фотографируем, и куда мы присылаем?
Я скину ссылку на Dropbox.
Окей.
А можно тогда еще вопрос из двух частей? Если в оверлифе можно, почему тогда нельзя в Notion? И если тогда такой электронный формат, что тогда, ну вот там по идее ссылка, то что с этим делать?
А что за ссылка еще разочек?
Ну, ссылка, на которую, то есть в оверлифе док, да, с которым, ну там окей, можно и PDF-ку. Ну хотя окей, Notion тоже можно, в принципе, экспортить PDF. То есть просто экспортить PDF и присылать? Или...
Ну да.
Окей. Ребята, подключайтесь. Напоминаю, завтра принести студенческие без обложки, а то потом будет проблематично продлить.
Так, можно же начинать демонстрацию включать. Демонстрацию экрана, а не какого-то окошка. Так, ну все, 9:31. Ты не успел, ты опоздал. Okay, so the time is up. Please, everyone, share your screens. And after this is done, I'm sending the text of our task to the Zoom chat.
Так, а если на бумаге писать, потом просто фотки, да, прислать?
Yes, I'll send you the link for the Dropbox where you'll be able to send it. I've sent the tasks for a Zoom chat, and I will also share my screen so that you can choose your own way of getting the tasks. So it's 9:31 now. Okay, let's have 25 minutes for this test. So at 9:57, we're over. Good luck, have fun.
Так, секунду, извините, а где еще раз задание?
В чате Zoom.
В чате Zoom или на моем экране. Можешь посмотреть, если ты его можешь включить. А, ты шаришь.
Да, мы когда шарим.
Понял, все. Спасибо.
I'm sorry to disturb you, but 2 more people need to share their screens as well.
Извините, а можно еще раз, где задание можно посмотреть?
В чате Zoom.
Я просто поздно.
Еще раз прости.
Все, теперь вижу. Спасибо.
Извините, я даже прослушал. А как мы сдаем работы?
Я сейчас скину ссылку на Dropbox.
Можно технический вопрос? Не копипастим же, да, задание, можно без этого.
Да, конечно.
Окей, я правильно помню, что ты насчет вот 4-й задачи, которая была вторая, которая про классификацию это букв, там можно нормально, ну, там можно, например, слои расписать торча.
Да.
Окей. А весь класс писать или можно просто слои?
Да нет, можно просто написать, сколько в каждой, какие слои получается и сколько параметров
Окей.
в каждом из них.
Окей. Ну, просто чтобы не рисовать, но при этом предоставить какое-то мое понимание того.
Но если время останется, то отлично. Если нет, в принципе, можно просто написать.
А сколько еще осталось?
Еще 10 минут.
Окей.
Да, рукописный скан может. By the way, there are 3 minutes left for the test. So in case you needed to finish something, I guess it's the best time now.
Почему 3 у нас же на 30 минут было?
Ну, 25, кажется.
Там просто было 25-30. Окей, что пишем.
Are these 5 more minutes required for everyone? Just send pluses for the chat in case you need some more time.
Well, the more, the merrier.
Okay, let's have it till 10:01, 02. But in this case, I'll have to catch some of your time of your break so that we can pass through all the material today.
А если не удается получить доступ к Dropbox, я могу скинуть пока работу просто в чат, а потом ее дозагрузить?
Да, давайте. Это не в
Спасибо.
чат, а мне в личку.
Сейчас надо, получается, в один файл, да, объединить фотки?
Да, можно не париться. Я разберусь, главное,
Понял,
назовите.
просто на имя и номер страницы.
Мгм.
Можно спросить, сколько еще я потерял фото времени?
Ага, еще 3 минуты.
Ты уже фотографировать, что ли, начинать? Или что?
Не, через 3 минуты можешь начинать фотографировать.
Окей, все.
Так, а если отправил, можно выключать видео?
Мгм. Okay, so the time is up. Please leave your pencils, take your mobile phones or photographs, and send the photos of your test to the link on the Dropbox. I'll resend the link once again to the chat.
Что в апреле произошла ошибка. Не следует поступить в данной ситуации.
Можно скинуть мне в Телеграме в чат. Ой, ну, в личное сообщение имею в виду.
Так, ну что, погнали учиться? Или как?
Yes, we'll wait till everyone send the photos to the Dropbox and then we'll start. Is there anyone who hasn't sent the test yet? Are we waiting for anyone? Okay, I hope not. So now let's start. Today we have we'll have a small overview of the computer vision field of machine learning. This is the most popular field of machine learning because the majority of current algorithms can deal with the tasks on the level which is similar to the one that people can deal with these tasks, or probably even better. The examples of CV are, well, the most popular ones are Face ID, for instance, on your mobile phones, or probably these Tesla or Yandex auto cars. They all require the model salvation of segmentation task each, I don't know, like 10 milliseconds, so that nobody is killed by this very car. But before we move on to the description of layers that the computer vision networks require, let's first recall one thing from the previous seminar, probably not recall, but speak about. I guess we have not seen this last time. So last time we were speaking about, well, we're not speaking about, we're speaking about it on Saturday, batch norm and dropout concepts. And these very layers, they were first invented for computer vision tasks. Batch norm for sure, dropout probably not, but it is used in all the computer vision networks. The very thing that we forgot to speak about is the order of putting the layers into your networks. So after we just learn that there are such layers like batch norm and dropout, totally have four types of layers that we need to have to somehow put in our network, and these are the linear transformation, just like linear, or sometimes it's called like simply dense layer. We have activation function, right? We have the batch norm layer. Oops. And we have the dropout layer, and the order of them is very important, since the incorrect order will lead to poor results. So it's important to know that generally there are two ways of ordering these very layers. The first one, which is the most popular, is as follows. First, we do the linear transformation of our data. Then we apply the batch norm. So in case there are some outliers in our data, they will be smoothed by the batch norm. And moreover, in case the initialization of some parameters was not good enough, the batch norm also solves this very problem. The next is the activation function. Oops, I'm sorry. The next is the activation function. The last one is dropout. Why in this order? Because activation function generally it does, well, ReLU for sure, zeros just generally 50% of the neurons, right? If we deem that neurons have the mean value of 0, then 50% will be less than 0, and they will be zeroed by ReLU. But all the other activation functions like ELU or GLU or leaky ReLU or sigmoid or hyperbolic tangents, they do not zero the other they do not zero any neurons except for those who had the values equal to 0. This is why after applying activation function, we'll have very small value, just number of zeros. And after applying dropout with probability p, we'll have 1 minus p. You can say it from p. So that totally we have about 1 minus p unzeroed values, right? So as p is usually taken like 0.1 or 0.2, well, in some rare cases 0.5, but nevertheless we have more than 50% non-zero values. And if we change their order, first we do the dropout, then the activation function, well, we will have the same number of zeros probably, yeah. But the problem is that for all those zero values will not have any activation function. So these are just like garbage for the activation function. We do not use them at all. So this is the most conventional way. And in case we're working with computer vision networks, after dropout, we apply the pooling. Today we'll speak about what pooling is. In other types of networks, we do not use this very pooling. The second way is just moving the dropout operation from this position to this, dropout, then batch norm, then activation function. I will not speak about the theory of this approach, but on some tasks, it shows really better results. And the investigation of the order is just a very hot topic now, because, well, theoretically, we can describe any results, yeah, when we see them, but it's with topics when something unpredictable turns out to be very good in practice, they are always of a very high popularity in science community. Okay, so this is the only topic I wanted to speak about from a previous class. Yeah, in case there are any questions, please feel free to ask them. Okay, so let's move to the computer vision networks. Well, they are usually referred to as convolutional networks, since all the current computer vision networks have a lot of convolutional layers, which are crucial for their performance. So let's pick what the convolution layers are and how these very convolutions can be applied for the data. Okay, so we'll use the materials of Stanford University today. We'll use some cheat sheets of them. I will send them to you after our class, because they depict perfectly the idea of convolutional networks. So some theory background. First of all, what the convolution layers are. I guess this can be better just depicted in the image below than described. So we have some filters. These are the parameters of our convolution layers, and for each, well, the size of this filter is a hyperparameter. In this case, it's equal to 3, and we apply it for each 3x3 piece of our image, as you can see in the picture, right? So for instance, the top left value of the output matrix is the sum of scalar products of each value of our filter by this top left 3x3 piece of our image, right? So which hyperparameters does this layer have? So first of all, it's certainly the filter size, and usually, and I would say in 90 or 95% of cases, the filter size is equal in both sides. So the only thing you need just this very matrix is a square one. The next one is this. Okay, and before we speak about the next hyperparameter, let's see how the convolution work just generally, because well, for me personally, it was like a novel thing after 2 years of working in convolution layers that, well, the filters are not two-dimensional tensors like this one. They are not matrices. Generally, the convolutional layers are cubes, and they look like this. So we have just filter size in our just length of the image, in our height of the image, and the third dimension is C. This is the number of input channels. So generally, our pictures are not black and white, they are colored. And since they're colored, we need several channels to depict the image. And for real world pictures, we use 3 channels. They are like red, green, blue, or some other types of color palette. Let's see how the convolutional the convolutional layer is applied to, for instance, an image with 3 channels. You can see the other demonstration now, right? You do, or you do not?
What do you mean by other demonstration?
I switched
this
to
is
another window.
Yeah,
Yeah, great.
Okay.
So it looks like this. We have this very matrix 3 by 3 for the first input channel, which is referred to red color channel. The same matrix for our green channel, the same matrix for our blue channel, and we also have the bias, just one bias. So how is it obtained? We multiply this very filter by each 3 by 3 piece of our red channel, our green channel for this matrix, blue channel for this matrix, and we add some bias. So generally, the number of units in and the result is just 3 by 3 matrix 1. So what we do is we combine information from all the channels to get the output representation, and this is the result of how one 3 by 3 matrix is obtained. And in case we want to just increase the number of channels, as it's usually done in our convolutional layers. So for instance, here we have 2 output channels, right? We had 3, now we have 2. And how will it look like? So we have these 3 by 3 matrices and the bias for the first output channel, and the same we have for the second output channel. And usually the convolutional layers are used to increase the number of channels. So generally this will be about 6 here. So there'll be about 6 output matrices, right? Which will be combined across the new channel dimension. Yeah. So what's the number of parameters in a convolutional layer? These are, from here we can see that for one output channel, we have this matrix consists of kernel size squared number of parameters. So all this matrix will consist of just kernel size squared multiplied by number of input channels plus 1. And just we have output channels number of this very constructions. So we'll have like kernel size squared multiplied by input channels plus 1 multiplied by the number of output channels. And this is the number of parameters in convolutional layers. Later today, we'll see that this is a big number, and we have to use some techniques to deal just to prevent from these networks from working for a long time. So in case everything is clear, the next hyperparameter which is used is the stride. And stride denote, well, you can see from here, it denotes number of pixels by which the window is moved after each operation. So here we can see the stride, for instance, equal to 2. Why? Because let's have the pause. So here we are just multiplying by this 3 by 3 square, yeah. And if the stride was 1, the next one that will multiply our filter by will be this 3 by 3 channel, starting with this 1 and ending with this 0, right? But instead, we can see it just jumps over this very square, and it starts with this one. So the stride is 2. So instead of moving by 1 pixel here, we move by 2. And again, the stride value is usually shared across length and across with dimension of the image. So you can see, for instance, instead of after we took this 3 by 3, instead of taking the next one, yeah, we jump over it for this very 3 by 3 square. So the stride reduces the number of the output pixels significantly. Just you can think of it that generally it reduces, just stride equal to 2 reduces the number of output pixels about twice. When the stride equal to 3, it reduces just like 3 times, and so on. That's not the exact numbers, but they're just good approximations. The next very important hyperparameter is the zero padding. And the zero padding refers to just extending our image with some 0 rows or columns, so that the result, the output result, will be will have more, will consist of more pixels. So as you can see from here, when padding is disabled, we only move across our very image. But what if we know that, for instance, in left top corner, the most important information can be presented? So we need, instead of taking this part only once, we can take it more times. So like this, we can do the zero padding, and we'll start from this very value. The gray squares here refer to zero padding. It has 3 general values, which are valid, same, and full. Same is also sometimes called half. So valid means disabling the padding. Same or half refers to making the padding of that very value that will, in case all the other hyperparameters are of standard values, like stride is 1, delation is 1. In this case, applying same padding will remain the size of the image constant. So in case we had a 6 by 6 image, like here, the output matrix will also be just for each channel, the output matrix will be of size 6 by 6. And the full padding means we want to just do as many convolution operations as possible, and we want to just apply it to each neuron as many times as possible. So here are the values for the full padding. A bit later today, we'll see all of them, not in practice, but better visualized. Okay, so in case no questions here, we'll move to the next type of layers. And the next type of layers is a pooling layer. Again, it's better visualized than described using words. And the best visualization, you could saw it on the previous link, and now you can see it here. So for instance, we have this very picture 4 by 4, right? So what padding does? Well, there are 2 best types of paddings, which are, oh, I'm sorry, not padding, for sure pooling. Yeah. So there are 2 best types of pooling, which are max pooling and average pooling. So what max pooling is what max pooling does, it just takes the maximum value of the squares, which is defined by the filter size. So let's speak about this very example. We have 2 by 2 just filters and the stride equal to 2. So we take, since the size is 2 by 2, we divide our picture by squares 2 by 2. And first we take the maximum value of the top left square 2 by 2, right? The value is 6, so this is our first output values. If this stride was equal to 1, the next square that we will apply max pooling to will be this one, 1, 2, 6, 7. But since the stride equal to 2, we jump over this square, and we turn out here for this square 2, 4, 7, 8, the maximum value equals 8, so we take it, and so on. So you can see that pooling operation is similar to convolution, except for that we do not multiply by any matrices, and we just take the maximum or the average value. Well, if we had the average pooling, for instance, here we would have about 3.25. Here we would have about 5.25 here, and so on. This is pooling, and well, you can see it does not have any parameters. It just makes some operation according to some rule. And the best order for them is making several convolution operations, just 1 or 2 or sometimes 3, and then applying the pooling after all these operations. And the purpose of using pooling is, first of all, to take the most important information, like when we take the max pooling, probably we'll take only those information which will be necessary for the network, and just remove the redundant information to reduce the dimensionality of the inner layers and reduce the complexity of our model. You can also see it here, just like how the average and the max pooling work. Here are some comments on them. And the last thing I want to speak about the layers is how the fully connected layer is used in convolution layers. So I should have started with this, but in computer vision, what is the dimensionality of a data? So while working with tabular data, like on our previous seminar, we saw that the data is two-dimensional. We have the number of rows, the number of instances, and each instance has some predefined number of features. So we have the number of instances and the number of features for each of them. In computer vision, the data is not two-dimensional, but it's four-dimensional. So first of all, we have a lot of images, and just like the number of instances, this is the first dimension. Next one is the width of our pictures. The next one is the length of our pictures. And the last one is the number of channels for all our pictures. So for like gray images, for black and white images, we have only one input channel. But for colored images, we have 2, 3, or sometimes even more channels that can well, probably not more, probably here I'm mistaken, but generally there are 3 input channels. So after we apply some convolutional and pooling operations, we need to somehow to just apply some linear transformations combined with activation functions to get some results for our model. And how to apply the fully connected layer for data if it's 3-dimensional, in just each instance is of 3 dimensions, while in general networks we have 1 dimension. We need to so-called flatten our images. So for a matrix, you can see the flatten operation here. We just revel it all the values, making it one long vector. And in case there are many input channels, just this very image has a lot of channels, we again revel it. So this will be the first channel, here will be the second channel, and so on. And for this reveled vector, we simply apply the fully connected layers, the linear transformations, as it was done previously, right? So, but this requires the flattening operation, and after applying the layer, we lose some information about which neuron referred to left top and which neuron referred to just right bottom, for instance, or for some middle pixels, of our images. So the fully connected layers are used, just the process of applying the convolution networks are divided into two parts. The first part, it consists only of convolutional layers, of pooling layers, of batch normalization layers, which can be applied after convolutional operations, of dropout layers, and of activations. And this is called the feature extractor of a model. Its goal is to get the best feature representation of each image, so that the next part, which is called the classifier, will be able to just classify the images according to this feature extractor. So the second part is, right, the first part is the feature extractor, the second is the classifier, and the classifier does not have any convolutional or pooling layers. It just has several fully connected layers, which are used consecutively with activation functions and dropout between them. So this is the small review of these three types of layers in the computer vision: the convolutional, the padding, the fully connected layer, the number of parameters in each of them, and some remarks about each of them. I suggest you watching these materials very much, because they perfectly describe the most important concepts in convolutional layers. Some commonly used activation functions, and recently the GLU activation function has also gained some attention and is sometimes used in convolutional networks. Now let's see some types of tasks for computer vision and how they can be solved. So generally, there are three main types of object recognition algorithms, which are this one for image classification, like we need to say what is depicted on the picture, which class is presented in the picture. In case we know that there can be many classes, for instance, if we had the class DSBA and we have the class book, probably this will be referred to both of the classes. And instead of having multi-class classification, we'll have a multi-label classification task where several labels can be inherent to one object, right? So the next one is the classification with localization. So first of all, we need to detect what is presented in the picture. And second, we need to show the boundary box of this very object, so that we can see which place in our image tells the model that this is a teddy bear and not a book, for instance, and not a, I don't know, a wall, which is behind. And the last one is the detection family of algorithms, when we have several objects in each image and we need to detect all of them with showing the boundary box of each of them. The boundary box is just this very part of the image which is referred to this class. Here are some types of networks that are that deal in the best way with these types of algorithms. Well, probably these very techniques like non-mark suppression, YOLO, and so on, in case you want to work with computer vision, or you are so much excited and intrigued by this field, you can watch all of this and ask me if anything is not easy for you. For now, we'll stop here, because all these things, they require deep understanding of the basic techniques. And we'll move to our seminars. We'll have two IPython notebooks, but one of them will not have any code, and the second one will have code. So this notebook, yeah, let's make for now our class a bit interactive. And what this notebook will consist of there will be many visualizations here, and your goal is to detect which just what is the value of hyperparameters in each image, right? So you see the picture and you say, okay, like this is the first picture, and we see that there is no padding, right? Just it's not our input. Yeah, for all the images, the blue square is the input image, the green one is the output matrix, and here we can see there is no padding since the blue picture is not extended with any zero values. The stride equals to 1 because we do not jump over any values, we just apply these consecutively, right? So in case you have a lot of correct answers, I will slightly increase the mark for the test that we have written today. Okay, so the first example, this one, what's the value of the padding and what's the value of the stride here?
I think the value of the padding is 1 because we have like we add one more, how to say, like we add length of 1 padding to the blue square, and the stride is also 1 because we do not jump.
Great. And if, as for padding, if we recall, there were 3 general types, like the absence of padding, same, and full. Which one is applied here?
I think full padding.
Not. No, here we have the same padding since the size of the input image is just input square equals to the size of the output square. Why not full? Because if we had the full padding, we'll have some more zero values here, so that, for instance, this very value in the right bottom, right, it would be also attended to using this very square, so using the left top values of our filter matrix, right? But since it's not the full padding. Great, thank you. So the next, yeah, this is the answer. Yeah, the delation, we have not spoken about it yet. It will be soon. I'll describe what it is. And here it is. So the delation is not very popular hyperparameter, but in some tasks of computer vision, it becomes crucial, really. And for instance, in these Stanford materials, we haven't seen any notions about it, but it's important to know what it is. So you can see the application of delation here. So when there is no padding and the stride equals to 1, here is how each value of the output matrix is obtained. So instead of taking, for instance, for left top corner, this 3 by 3 matrix, we take this value. Since the relation is 2, we move not to the next value, but we jump over it, and we have this and these values. And just we do the same for length and with dimensions. So instead of taking the left top 3 by 3 square, we take the 5 by 5 square and take only the it's called odd values, right? So the 1 1 element, 1 3, 1 5, 3 1, 3 3, only the odd values of this very matrix. This is what delation is in convolutional networks. Okay, so the next example is this one. If there is anybody who wishes to answer, feel free. What's the value of the padding?
I think that the padding is 2. I mean, the full padding, no?
Yeah.
And stride is equal to 1 because we jump over 1 row, no? No, we're not jumping. Yeah. Yeah, the stride is 0. Well, 1. The stride is 1. We're not jumping.
Yes, great. Thank you. The stride is 1 since we do not jump over just pixels while applying the convolution. Here is the answer. And now the next example. Anybody?
So the stride is 2 and padding
Yeah.
is 0.
Yeah, great. Since we do not have any 0 values here. Okay, so let's move to this. Here, what's the values of the hyperparameters?
Well, destroyed is 2.
Yeah.
And padding is 1.
Yes, and is it a full padding or a half padding?
It seems to be a half padding.
Just there are half, I mean like same padding. Okay, so same or half padding refers to the value of padding which is necessary for our image to be of the same size that the input image in case all the other hyperparameters are standard. Well, here we can see the stride is not standard, and to get the value of the half padding, so to understand how much do we need to pad our image to have to be of like same padding, we need to imagine that the stride would be equal to 1. So the size of the input image is 6 by 6, and in case the stride would be equal to 1, in this very setting, after applying this padding, we would have the 6 by 6 value of the output image, right? So, okay, so let's see the answer. The padding is same here because just the value of our output matrix would be 6 by 6 if the image if our convolution had stride equal to 1. But since it's having stride equal to 2, we need to have the output image twice less than it was. You could also see that here, for instance, since the stride equals 2, we do not use this very padding, so it's just unnecessary for us. It would be used in case the stride was equal to 1, but since it's 2, it's just not used, it's redundant, we can remove it. Okay, so before we move to our next examples with transposed convolution, let's first see what it is and what's the purpose of it. Yeah, but before we move to the transposed convolutions, let's see how the convolution operation can be made as a matrix multiplication. So this very operation, I guess it's just understandable for all of you, but probably it's not very easy to understand how to integrate them into neural networks. So how to make this operation differentiable. Yeah. So what is done in neural networks when applying convolutional layers is as follows. So this is the kernel of our convolution, which will be applied to each 3 by 3 box of our image. First, well, probably this is not the best word here. We do not rearrange, but we construct a matrix which consists of just the number of rows equals to first we calculate what the shape of the output image will be, and we make a matrix which has the same number of rows that the number. Okay, I will later describe why we take the 4 value here. And here the value of 16, because we will need to revel our image. So in case instead of applying this to matrix, we'll just multiply this by the reveled image, by the flattened image. And since the size of the flattened image equals to 16, the dimension here equals to 16. How do we construct this from this? Just why this very order of zeros, not some other orders? Well, we'll not stop here in case this is difficult for you. probably think this is. Here is a small explanation how to construct this matrix. And if you want to deepen into this, you need to just take one picture and see what's the value that each pixel of the image, of the output image is constructed. So how to get each value of the output image, and you'll see that this is just how do we need to apply it. For instance, here we had just the absence of zeros, 1 for 1, 0. Here we have 0, 1 for 1, because this very operation like 3 by 3, like, okay, let's take this very example, because no, the first one, we applied it for this square, and then we move on, and just the first column, the first just several values of the first column, they will not be attended to. So for the next operation, we just zero this value since we will not attend this. Okay, so after we constructed this convolution matrix, what we do is we flatten our input image. So if we had it like this is how it will look like. So the first row concatenated with the second row, and so on. In case there are several channels of our image, they will be again concatenated. So here will be the first channel, then the second, and so on. What we do next is, well, first we calculate the shape of the output image, and we just have calculated that using the matrix 3 by 3 for our input of shape 4 by 4 with stride equal to 1, padding equal to 1, we'll have the output 2 by 2. So 2 by 2 is reveled to 4 by 1, and this is where this very 4 is taken from, and this is why the shape of the convolution matrix equal to 4 by 16. And so we multiply the matrix by the vector, and what we have is the vector of shape 4 by 1, then we rearrange it back, and this is how the convolution operations are applied inside the neural networks. Okay, so let's move forward. And another very important task that is of probably the biggest popularity in computer vision is the segmentation task. So what is binary segmentation task? What is multi-class segmentation task? Binary, we have only one object, predefined object. So for instance, this is the task of classifying, I don't know, animals or mammals, or probably the zebras. And here is the answer. So this is the zebra, and this is, we need to just segment this very zebra or animal, if the task is to segment the animals, just with white pixels, while having the black pixels for all the other objects. For instance, here it just did not notice the second zebra in the image. No, that's okay. The multi-class segmentation task is the one that is solved each 1 or 5 or 10 milliseconds in autocars of Tesla and Yandex, and this is the example. So we can see with the purple the road, with the white some, I don't know how to say, is разметка of the road, with blue the cars, with red the people, yeah, and so on. Some video demonstrations like how this is applied. Well, on each second it segments, like when the dog is running, here is the dog, here is the tree, and so on. There are some demonstrations on the cars as well. And now there are some questions for you for this very task. First of all, what's the input for the network, and what's the output for such a task? Well, the
video is an input.
Image is an input.
Pixels
Yeah.
are the input.
Matrix of pixels.
Yeah, the images are certainly the inputs. We cannot classify the video. We can just classify the image on each, obtained on each several multi-seconds. And what's the output in such a task?
Well, augmented image too.
Why augmented?
Well, we have to highlight the what's that? Like on the video, we have to highlight the classes in different colors.
Yeah, we highlighted, but that's not augmented. The augmented images will refer to some other types of images. Probably will have time to see them even today.
Well,
Okay.
if you change the colors, you augment it too. So just
Yeah, so just the output is the same image, but it's now colored. So each class is colored with its own color. Yeah. So for an image of shape NM3, what's the shape of target? Well, that's easy. So in case we
Sorry, maybe the same.
Yeah, the same. I did not understand you at first. Yeah, great. So the shape of the target is the same since we want to color each just object. So there it is. And for a binary segmentation task, the shape of target will be NM1 because there is no need for colors. Like here, we can just use the black pixels for all other parts of image and the white for the object itself. What does the target consist of? We've already spoken about. What's the activation function loss for a binary segmentation?
Sigmoid. Maybe.
Yeah, and the loss?
Entropy.
Yes, binary cross entropy. We call the log loss. Oh my, it was the charge. Okay, so and what's the activation function loss for a multi-class segmentation?
Maybe a softmax.
And the loss?
Don't know.
No, the loss is the same for all the multi-class tasks of machine learning. It's the cross entropy. Yes. And another question which can be very important on different interviews. For instance, I have heard it twice or probably 3 times for multi-label segmentation task. What's the shape? What's the activation function used in the end, and what's the loss function? Just the difference between multi-class and multi-label is that each just value can have several labels inherent to it. No one knows. Okay, so for now, multi-label task requires the usage the same as the binary task, just sigmoid activation function and binary cross entropy as the loss function. Probably later in our course, we'll see why this is true. Okay, so yeah, we're already out of time. So let's do the following thing. For now, we'll see how the segmentation task works, which layers does it require, and the notebook with some code I will just send you. You'll have a look at it, and the next class will start with it. So well, we have 2 seminars for computer vision, and on the second we'll see the code, how this can be coded. Yeah. So speaking about our task, we have some kind of input, like these 2 cows. We need to extract the features from it and get the picture of the same shape as it was. Well, probably losing the first the channels in case just we don't need them, but
well, this depends. But anyway, we need to somehow apply about 8 or probably 12 or more convolutions for an image. And if we do not decompose our image, if the size of the pictures remains the same, like H and W, the size of the intermediate layers will be very large. And as we saw here, the kernel 3x3 requires decomposing for 4x16 in case our image is of shape 4x4. And if our image is like this, of shape like 64 by 128, you can imagine the size of this layer. It will be just immense. It will consist of this matrix of more than several million parameters. And of course, this very part will just take eternity to work. So to extract our features using several convolutions and decompose our picture, our images to just accelerate the process of working, we need to do the downsampling first and then the upsampling. So first we decompose into some small dimension, like here, for instance, H divided by 4 and V divided by 4. And then we upsample, so we recompose back our image to its original shape. This is how it's usually done. So we have several convolution plus batch norm plus ReLU plus dropout layers. They are marked with blue, just 2 consecutive blue layers, yeah, and then the green layer, the pooling layer. And you can see in the image that generally it's just pooling layers which reduce the dimensionality. So as we could see here, having this stride of 2 just shrinks the dimensions of image twice. So 4x4 will now have the shape 2x2. And this is how pooling usually applied. So generally, we use 2x2 pooling to decrease the shape of image twice, yeah, each dimension. And then we do the upsampling. And in upsampling, the order is just reverse. First, the pooling upsampling layers, and then 2 consecutive upsampling convolution plus batch norm plus ReLU. But how to restore the dimension? Okay, we know how to decrease it, but how to restore it? The first option is like this. So, well, I do not know what this image refers to. I guess I lost some good image here. Okay, I will tell you this. Several options. First of all, is just nearest neighbor. So we had 1, 2, 3, 4. Okay, let's fill, make it of shape 4x4 and fill each square with the corresponding values. So here will be all 1s, 2s, 3s, 4s. You can see it here. The second is the bed of nails. So do the same operation, but instead of filling with the same values, we'll fill them with zeros. But both these techniques, they're very simple and we'll probably lose some information after applying them in upsampling. Another primitive technique, but the best among all of them, is the maximum pooling. So, for instance, here we had some 5, 6, 7, 8, just rest of the necklace, and now we have the 1, 2, 3, 4. What we do is we do the same like in bed of nails, but we restore their positions. So we remember that this very position was the biggest one in this left top square. Yeah, so we fill this very value with 1, and all the other will be 0. So like clever bed of nails. But the best option is to use the transpose the convolutions, and for now we'll quickly see how they work. So previously, we used to multiply the matrix of shape 4x16 to get the 4x1 output, right? And now let's do the reverse operation. We'll multiply 16x4 matrix by 4x1 input to get the 16x1 output. And then we will just reshape it, getting the bigger output matrix. And this is how it works. So we use some padding, and this is, well, generally it's the same as convolution, but we use some padding, and in fact we will well, I don't know whether we'll see it or not, but this is the same as multiplying each value by each, just taking this very kernel matrix and multiplying each value by it and summing them up. Probably, yeah, I'll show how this can be done. But for now, we can refer to it as just the modification of convolution with some hyperparameters, which can just increase the number of the input image or the shape of the input image. The last important theory thing about the transposed convolution is not the last, two last things. First of all is how this stride is applied. So for instance, here the stride equals to 2. It's the mistake here. Not of course, I'm sorry. It's for the next one. So you can see in the image why this just when the stride is 2, how is it applied? So we divide the input pixels by empty lines and columns, and this is how we use the stride. And interesting thing that in transposed convolution layers, the padding refers to, if previously we used padding to increase the shape, now the padding is used to decrease the shape. And in this very simulation, the padding equals to 0. And if the padding equals, for instance, to like same, we would have only this very box of shape 4 by 4. You can see the cursor of mine, right? And if we had no padding, we would have only this 2 by 2 image, which is once multiplied by just this square. Okay, so these are what transposed convolutions, and applying them results in very accurate and precise upsampling and leads to good results in segmentation networks. So just 3 more minutes of your attention. I'll send this notebook with a classifier. This is an example from PyTorch. Here, the popular CIFAR10 dataset is used, and they just show how to run a primitive computer vision network. So we upload some data using the Torch. We use the Torch Vision library here. We upload the data using the just inbuilt CIFAR10 class. CIFAR10 refers to a very popular data set with 10 classes. Yeah, so we make some transformations for our images. Here is how they look like. Here is, for instance, the plane, the bird, the car, the cat, right? Here is the example of a network. Like we can see, again, convolution first, then the activation function ReLU, then the pooling. Again, the convolution, then just the next convolution, yeah, the ReLU, the pooling. Why do we have the same self-pool here and here? Because pooling has no parameters, and when the kernel size of the pooling is the same and the stride is the same, we can just use the same attribute of our network. Then we flatten the input. So here the feature extraction part is over, and now the classification part starts. We use the fully connected layer ReLU, fully connected ReLU, and the last fully connected layer. Just cross entropy loss, since we have the multi-class classification, SGD, or we could use the ADAM here. We train a network for 2 epochs here, and then when we see the results, like here are some arbitrary images. You can see here is the cat, the sheep, and the plane. And here are the predictions of the network. So 50% are right, cat and plane are right, and for sheeps, it's mistaken. Then they just see the total, just this is the evaluation loop. They see the overall accuracy on 10,000 images from test, because the CIFAR10 dataset is very large, and just measuring the quality on all of it would require a lot of time. Here we see the accuracy for each category. We can see that, for instance, deers are classified very poorly, and ships are classified very well. And well, ships have the best quality for classification, and it's even strange why for these two ships our network was mistaken. Okay, so we'll just deepen into this notebook and see it more precisely on the next class together with outer encoders and probably the tracing method. For now, I think that's over. Yeah, if there are any questions, please.
Did you say that we're going to discuss autoencoders next week?
I'm sorry?
Could you please repeat what we're going to discuss next week?
Yeah, next week we'll first of all look through this notebook and see how some operations which are trivial for you are applied. Then we'll speak about the autoencoders and also see an example of them. But for in your course in the week 4, we have some just application of autoencoders for computer vision tasks. But autoencoders are not only applied to computer vision tasks, and the most general application of autoencoders is now the recommender systems, which is just a separate field of machine learning. I guess it's also a very important one. And since we are having an introduction course, I need to get you acquainted with all the just spheres of machine learning. This is why after looking through the seminar, we'll look through the notebook devoted to application of autoencoders for recommender system tasks. And then if we have some time, we'll speak about the track-in method. Well, I don't know how it's correctly pronounced, either track-in or tracing method, which is just a state-of-the-art method from Google for detecting the outliers and measuring the influence of training data on our test data. But for now, just IDM will not have enough time, so probably track-in will postpone for our class number 5.
Okay, thanks.
Okay, so if there are no questions, thanks everyone, bye-bye. And group 182, we have 4 more minutes for you to prepare for a future test.
Thank you. Bye.
Bye.
Аким, можно вопрос?
Да, давай.
Мы, получается, пишем его и тебе в ТГ кидаем? Или как?
Сейчас я скину ссылку на Dropbox, расскажу про это все.
Окей.
Да, пишем, получается, полчаса, потому что в предыдущей группе полчаса писали. И, ну, на самом деле, да, за 20, ну, особенно если кто-то будет ехать вдруг, то за полчаса явно не... Ой, за там, 25 минут сложно это успеть, лишние 5 минут будут ценными. Вот, затем поговорим про computer vision задачки.
Есть, очень хорошо видно.
А?
Да не, там парень подключил камеру.
Да, смотрите, по поводу камеры и всего этого дела. Во-первых, нужна будет ваша камера демонстрации у всех. Во-вторых, я верю, что вы все прекрасные и красивые, но чтобы как бы был какой-то процесс контроля, нужно, чтобы ваши руки были в камере, потому что как бы, можно ее чуть-чуть поднять, да, и спокойно сидеть в телефоне. Я это сам прекрасно понимаю, поэтому вот такая просьба.
А мы все просто запускаем демонстрацию экрана, да?
Okay, so let's start. I hope everyone is, well, not everyone. Please, everyone, enable the demonstration, the share of your screen, and please share the full screen, not only one window. I know how the sharing of one window looks like. Okay, so I will send the task for a Zoom chat.
Мы звук включаем или без?
No, the sound is unnecessary, not to disturb all the other ones.
Да, можно быстрый вопрос, ну, чтобы потом претензий не было. Все в порядке? Нормально сижу?
А как тебя зовут?
Анатолий.
Анатолий. Ну, чуть-чуть пониже можно камеру опустить, и так замечательно.
А куда в итоге потом работу отправлять?
Работы отправляем в Dropbox. Я скину ссылочку. Всем дозираем. Все. Задание в чате. The task is here. We have 30 minutes, so in 11:43 we are over.
Блин, а можно ссылку на чат? Я его не вижу.
Сверху просто посмотри, там, подними мышку, будет чат.
Где?
Наводишь мышку на там, где написано «Я демонстрирую экран» или что-то такое. Там у тебя будет чат.
А, здесь чат, я думал в телеге.
Здесь.
А у меня точно тот файл? У меня 181 группа написана.
Да, тут файл, потому что я не менял всякие задачи.
Сколько времени у нас еще осталось?
17 минут.
Можно попросить продублировать ссылку на Dropbox в телеге, пожалуйста? Спасибо. А какие требования по названию файла?
Фамилия группы.
Так, я закончил, сканирую, поэтому беру телефон. Такой быстрый вопрос. Если я 181, но пишу 182, мне писать все равно 181?
Да, чтобы я его нашел.
Что-что?
Ну, этот номер нужен, чтобы я его нашел просто.
Да, хорошо. Фамилия и номер группы. Все, да?
Можно встать за телефоном, да?
Если загрузили файл, то все, можно отключаться. Ну, точнее.
Это ок, что там ссылка на тест 2.
Это я ошибся, наверное. Ну, нормально, тут закажу.
Так, а вы можете, пожалуйста, проверить, получили ли это меня?
Да.
Все в порядке?
Мгм.
Так, хорошо, можно отключаться тогда, да?
Мгм.
Ничего, если мне не получается переименовать файлы?
Ну, главное, если странички.
Мгм.
Okay, so for all who is still writing, there is 1 minute left. If you had to finish anything, this is the perfect time.
Карин, все загрузилось, не переживай.
Так, есть кто-то, кто еще не загрузил, кого ждем?
Да, сейчас я загружаю. Секунду.
Да, если что, писать нужно перестать, если кто-то еще этим занимается, и начинать фотографировать.
У меня вынужденные меры, у меня не присылается никуда. Можно я отключу экран?
Ты можешь скинуть мне в Telegram.
Давай. Я не могу. У меня почему-то пропала штука, чтобы я могла из Ленса кинуть в телегу. Я обычно себе перекидываю. Сейчас у меня не получается. Я не знаю почему. В Suggestions
Тогда
тоже нет.
кинь в Zoom.
Я могу кинуть сразу в Dropbox.
С плохим названием можешь сделать так. Это не страшно.
Ага, окей. Это странно. Это грустно. Так. Оно не оно. Блин, не оно. Если я просто... Сейф.
Так, заканчивая тогда с отправкой. Okay, for all the other ones, if there is anyone who still hasn't sent, please do it as soon as possible. We have a lot to discuss today, so let's start. We'll probably need some, I don't know, like 10 or 15 minutes from your break, as it was from the previous group, to have everything discussed today. So before today we will discuss the computer vision networks. We'll see which types of layers are used there and how these layers are applied, how they're used. But before we move to this very topic, we need to revise the batch norm and dropout from the previous class. Namely, we need to, okay, let's open another sheet of paper. We need to, the only thing which we have not discussed last time was the order of integrating all these layers into a network. So generally, neural networks, for when we do not have special tasks like computer vision, natural language processing, for instance, we have 4 types of layers, which are linear layer, which is an activation function, right? Which is a batch norm, which is the dropout. And in convolutional networks, we also have new types of layers called pooling layers. We'll speak about them today. But in other tasks, it's used very rarely, only for speech recognition. So what's the true order of using all these layers in a network? There are 2 ways. The first, the most just conventional one, is the following: using the linear transformation of the data, then the batch norm, so that in case there are some outliers in our data or they will be smoothed, and in case the initialization of the parameters of the previous layer was not very precise, the batch norm will also correct the result of the linear layer. The next is the activation function, and the next one is the dropout. Why these 2 layers in such an order? Because, well, if we forget about ReLU for 1 second, we'll see today that in computer vision especially, and in some other tasks as well, some other activation functions are also used, some modifications of ReLU like leaky ReLU, ELU, or GLU, and in some other networks, more rarely, of course, but anyway, sigmoid and hyperbolic tangent are used. And all these functions, except for ReLU, they do not zero any values. So they can diminish some values, they can transform them to other diapasons, but they do not zero them. And if we first zero them and apply the dropout, then instead of just having several 0 values, what we'll have is some values will be like, they will be transformed by our activation function. And instead of having, like in this construction, if the dropout probability is P, then the number of zeros equals to non-zero values after this sequential construction equals to 1 minus P multiplied by the number of total neurons, right? Because activation functions have not zeroed any of them, only the ones which were equal to 0, and it's impossible since we are having the batch norm here. And the dropout just zeros P of them. And if we change the order and first apply the dropout and then the activation function, then after the activation function, let's say we're having sigmoid, 0 value will be transformed to 0.5, for instance, and we'll have 0 values. Okay, so there'll be no 0 values in such a construction. Of course, the other functions, ELU, GLU, even tangent, hyperbolic, they 0 values will correspond to 0 values after applying this very function. But instead of just zeroing some values to prevent overfitting, we'll be like corrupting our input, and this will lead to poor results. The second way, which is much more rare, but anyway, it's it was explored about 2 or probably 3 years ago, and it was found it also can be exploited. It's like using linear, then dropout, then the batch norm, and then the activation function. For now, just the theoretical description of such an order of the layers is very vague, and well, it describes deep learning very well, that sometimes some constructions which should be awful from the theoretical point of view, they turn out to be beneficial in practice. So, well, in case you see such an order of the layers, don't be surprised. It's also applied somewhere, and just there are some examples. For instance, for this very popular dataset NIST, where this construction leads to better results. If we deal with computer vision networks, after this, everywhere we'll have the pooling layers. It's always used in the end. So that's all I wanted to speak about the order of dropout and batch norm. Now let's move to our computer vision networks. I'll take away the interactive desk. Please tell me if my screen can be seen now. It is, right?
Yep.
Great. So yeah, let's speak about the computer vision networks. They are often referred to as convolution networks because they have a lot of convolution layers. And what is the convolution? How are these convolution layers applied? I guess it can be better visualized than spoken about. So here is how the convolution layer works. We have this matrix of filter size, right? In our case, filter size equals to 3. And this is a hyperparameter of this layer, and we apply this box 3 by 3 sequentially for each value, for each box 3 by 3 of our image. So for instance, to get the top left value of the output matrix, we need to multiply this filter by the top left square of our input image, this one, yeah. But generally, they look a bit different because we often work with images which are not black and white, and to present an image to make it a colored image, we need several channels through which to show it. For instance, the most popular setting is the red, green, blue, referred to RGB color palette. And we have several channels. So our filters look like this. This is the filter size, and this is the number of input channels. So let's see how this can be applied for our image. Okay, we'll wait for 1 second. Yeah. So we'll have, since we have 3 channels, 3 input channels, the red channel corresponding to red color, corresponding to blue color, and to green color and blue color, right? Red, green, blue. Yeah. So we have 3 matrices, 3 filter matrices. The one for red channel here, the one for blue channel here, the one for red channel, green channel, blue channel. Yeah. So to get just 2-dimensional matrix, to get 1 output channel, the first matrix, how will it look like? We need to multiply the filter, the red filter for the red channel, the green filter for the green channel, the blue filter for the blue channel. Let's wait for about 15 seconds so that the movement moves to the one we need. There it is. So We take the image from the red channel, multiply it by our filter corresponding to red channel, and sum it up with the ones for blue and red and green channels, and add some bias. So for one output matrix, we have one bias value. So multiplying this by this, summing this up, and doing the same for all the other channels and summing up with the bias, we get the first output value. This is, for instance, 0, right? We do the following operation, moving our filter, and we get the output matrix. So this is, but generally in convolutional layers, we want to increase the number of channels so that we can get the representation of our image from different sides. And usually the number of output channels is twice as big as the number of input channels. So we need several output matrices, like generally we would have here 6 output channels, since here we have 3, now we would have 6. So we need to have these just number of matrices for each filter, for each output channel. This is the setting for the first output channel, this is for the second, and so on. So the number of parameters in such a layer, in convolutional layers, equals to, okay, let's get back here. Filter size by filter size for one matrix, input channels number of such matrices, right, plus bias. So this is the number of parameters to get the output representation for one channel, which equals to filter size squared multiplied by number of input channels plus 1. And since we have output channels number of such constructions, yeah, the total number of parameters in convolutional layers equals to filter size squared multiplied by number of input channels plus 1 plus bias multiplied by the number of output channels. We'll see it again later. So this is how the convolutional layers work. And as for the other hyperparameters apart from the filter size, the first one is stride. You can see it here. The stride denotes the number of pixels by which the window moves after each operation. So in this very example, we have the stride equal to 2. Why? Because let's see, now we're here. And if the stride was 1, just the default value, then we would move our filter matrix to this very squared, starting from this 0 and ending up with this 0, like 0, 1, 0, and so on. And we would multiply our filter matrix by it. But instead, if you look here, we move, we jump over this square and move to the next one. So we were here, and now we're here. We jumped over the next square. And since we jumped only over one square, the stride equals to 2. So instead of moving by 1 here, by 1 pixel, we have moved by 2 pixels. This is what stride refers to. And usually, yeah, that's the same for filter size and for stride and for all the other hyperparameters. If we set the value for filter size equal to 3, then in 95 or probably 99% of cases, we'll have the matrix will be squared. So 3 across the length dimension and 3 across the width dimension. The same logic can be applied for stride. So if we set stride to 2, we can see that we are starting from this square, yeah, and instead of next moving to this square 0, 1, 1, we move to this 0, 0, 0. So we jump over this very row, right? So this is how the stride works. Another hyperparameter, not the last one, is the zero padding. It is applied to either attend to as much as possible to each pixel of an image. For instance, we know that in our images, the most important information can be contained in the right button of our image, somewhere here. And if no padding is used, we'll only once attend to this very pixel, for instance, yeah, when taking the convolution of this. And only twice these very pixels, which can contain very important information for our classification or detection or something else. So we can do the padding, the zero padding. So just concatenate 0 columns and rows to a matrix so that the filter will also attend to this, like you can see in this image, and no information will be lost. In addition, sometimes we want our image to preserve the length and width values, because when applying without padding, like here, the output, even with stride equal to 1, we would have 1, 2, 3, 4 pixels across each dimension here. And if we want to preserve the dimensionality of the image, then we need to do the padding from here and from this side, so that the shape of the output image will also equal to 6 by 6, and we preserve the dimensions. There are 3 general types of padding, which are valid, same, and full. They are often referred to like this. So valid means no padding, same means do this such amount of padding that the number or just the shape of the output matrix will equal to the shape of input matrix in case all the other hyperparameters like stride and deletion, we'll speak about deletion a bit later, in case they are default. So like this. So padding such that the feature map size has size taking the integer part of input shape divided by stride. Yeah, so that's the value of padding which we need to do to get the same padding. And full padding means we want to attend each pixel in the image as much as possible. To tell the truth, it's not the very correct representation here, because for full padding we would also have a 0 column here, so that the right bottom value of the filter matrix of convolution matrix would attend to left top value of our image. Yeah, so this is what full padding is. Okay, so if there are any questions, feel free to ask them. If no questions for now, let's move on. And the second type of special layers is the pooling layers. Again, it's better see it's visualized than spoken about, like here. The purpose of pooling layers is to reduce the dimension of our image, preserving the most important information. So, well, that's for sure that when we just diminish the dimensions of our image, diminish its shape, some information will be lost. But the goal is to lose as little information as possible, and here is just pooling is the best way of doing this. There are 2 most popular types of pooling, which are max pooling and average pooling. Here is the example of max pooling. So how is it applied? Again, we have some filter size, usually 2 by 2 values taken, and some value for the stride. So the first step, there are no parameters in pooling, so just 2 by 2 filter refers to the size of the boxes onto which we will just cut our image. So first 2 by 2 box, since we have 2 by 2 filter here, we take the maximum value of it. It's 6, so we move it here. If we would have the stride equal to 1 here, then we would move to this very square 1, 2, 6, 7 and take the value 7 from here. But as we are having stride 2 here, we jump over it, and the next square is 2, 4, 7, 8. The maximum value is 8. We take it here, and so on. Here the maximum value 3. We take it, and this is how max pooling works. Usually the number of filters is either 2 by 2 or 3 by 3 in some more rare cases. And it's stride which helps us reduce the dimensionality. So the stride equal to 2 means that we will decrease the length, the number of pixels across the length and width dimension twice. Yeah, so it's very convenient that we can so easily decrease the dimensions of the image without losing too much information, preserving the most important. Here is how pooling works. Here is the example of max pooling again and the average pooling. So yeah, in average pooling, instead of taking the max value of the box, we will take the average value of the box. Okay, hope no questions here. Let's move to fully connected layers, because previously we saw the examples of using neural networks with tabular data, and the tabular data is two-dimensional. So we have the first is the number of instances, right? And the second is the number of features of each instance. So 2 dimensions. And for images, we have 4 dimensions. Why 4? Because first of all, we have the number of instances, the number of images. Yeah, that's the first dimension. The second is the length of each, or just the height of each image. The next is the width of each image. And the last one is the number of input channels. For instance, for colored images, we have 3 channels, right? So, and fully connected layers, they are referred to matrix multiplications, right? So we need to somehow just reshape our input so that each image, which has 3 dimensions, will be now represented as a vector which has only 1 dimension, the length of this very vector. And to do this, we use the operation called flattening. What we do for one matrix, yeah, if here is 1 channel, we just revel it, flatten it into 1 vector, taking these 3 elements first, concatenating with the second row, with the third, and so on. And if there are several channels, then this will be for the first channel. Here we'll have for the second channel, for the third, and so on. Here is how flattening works. And now when each image is represented as a vector, the same as with tabular data, we can apply the just matrix multiplication, pass it through the fully connected layer to get some just important features for our data to classify. And generally, the convolutional networks are divided into 2 parts. The first is the feature extraction, and the feature extraction does not have any fully connected layers, since we see here that we need to flatten our input, and so we lose this information like which neuron was the left top corner, which one was the middle pixel in our image, which one was the right button in our image, and which is referred to which channel, and so on. This information will be lost when flattening, applying the just dense layer here. This is why the feature extraction part consists only of convolutions, of pooling layers, and some general layers like batch norm, dropout, and activation functions, which do not require our data to have the 2-dimensional view, right? And so the next part, the classification part, it gets as an input this very just feature extracted by the feature extractor, yeah, and they pass it through several fully connected layers with activation functions and dropout layers between them to get the output result. Either this is the classification task, then the just the probability of each class, or I don't know if this is some more difficult task. Again, probably the output will be of some other shape. But anyway, we pass it through the fully connected layers and get some output value. This is how the convolutional networks are divided into 2 parts. And now let's quickly see the some tasks where the computer vision is applied. By the way, this is a very convenient cheat sheet from the Stanford course. Yeah, and while preparing for the next work, or probably when you're preparing for some interviews, it's very convenient to look it through and get just quickly very important things from here. There are generally 3 main types of object recognition algorithms. First is image classification, like there are several predefined classes like teddy bear, I don't know, something like other animals, people, or books probably. And we know that we have one or sometimes more label, just in case of multi-class classification, we have exactly one label assigned to each image. For instance, here is the teddy bear. And if we would have the multi-label classification task, probably we could have several classes inherent to each image. And for this one, we would have both teddy bear and book classes. But anyway, our task is only to understand what is depicted in the picture. Next one is classification with localization. So we know this task can be only applied when we know that precisely one value is inherent to each object. And here we see is the teddy bear. But instead of only predicting the class for the image, we also need to output the boundary of the object in the image, which told our model that this is the teddy bear, for instance. Yeah. So if it outputs the book and calling it teddy bear, we would have a very big loss value here because, well, it detected the bear correctly, but the boundary box was not correct. And the idea is to understand where this very teddy bear is present in the picture. And the last type is the detection. So there are many objects in each image, and we need to detect all of them. We need to set their boundary boxes, and we need to assign labels to each boundary box. For instance, this is the teddy bear, and this is the book. Here are some examples of CNN types which can work with each of the tasks. Yeah. Later, if you feel that computer vision, you are just intrigued, you're excited about computer vision, you want to devote your life to it, it's just very good to look through all the other topics discussed here, like non-mark suppression and so on. And I will not speak about them, but if you have wish and you decided to do it and you have any questions, feel free to ask me just in Telegram and chat. I will describe all of this. Yeah, so if there are no questions here, let's move on. We'll have 2 notebooks for today, but the second one we'll just look through and discuss it next time. And the one which we are going to discuss will not have any code. So let's speak about convolutions, and the same as we did with group 181. Your goal will be we'll have some interactive part now. Your goal will be to tell me the hyperparameter values for each image. Like here, for instance, we can see this is the convolution operation. Yeah, in all the images, the blue matrix is the input one, and the green matrix is the output one, and this shadowed matrix is the filter of the convolution. So this is the first example, and we can see that the padding equals to 0, since we do not extend our, we do not enhance our image with some 0 values. And the stride is 1, since every time we move by 1 pixel across width and across the height dimension. Yeah, but before, okay, no, not before. Okay, so the first example is here. Like usually, the ones who answer correctly will have some small increase for our today's tests. So if you feel you're good enough, please don't hesitate to answer. No one will tell me what's the padding and stride values here. Well, okay, let's look through it together. So the padding value equals to 1 from each side. The stride equals to 1, since each time we move only by 1 pixel in each side, right? And as for the padding, yeah, it's not just very correct say padding is 1, because usually the padding is set to these 3 default values, which we have looked through. And here the padding is same, or same value is sometimes referred to as half, because the size of the input image equals to size of the output image, right? So we apply such a value of padding that we preserve the dimension of the input image. Okay, we'll see now how the last hyperparameter, the delation, works, and get back to the interactive part. I hope some of you will answer for these images. Okay, so for delation, this is the most novel new hyperparameter, because you could see that in Stanford materials they even didn't pay attention to it. But for some types of networks, it's very important, and let's see it. So instead of multiplying our 3x3 filter matrix by, for instance, this left top square getting the left top value, what we do is we make strides, but we make strides not while moving our filter window, but when taking the value, the matrix for our input. So instead of taking 3x3, we take only the even value, the odd values here, like 1, 1, 1, 3, 1, 5, 3, 1, 3, 3, 3, 5, 5, 1, 5, 3, 5, 5. Yeah, only the odd values of our matrix and multiply by them. And sometimes when the image is of very high resolution and the neighbor pixels are almost always the same, delation helps us to get some more information that we would get using just without using a delation. This is how it works. Here is the representation. Okay. If there are any questions, please ask them. If no questions, let's move on and get back to our interactive part. For this example, can anyone please tell me the value of padding and the value for strike?
Padding is 2, yes, I think.
Yes, and if we used the previous default values like no padding, same padding, and full padding, which one is applied here?
I guess same, no?
Well, not exactly, because we can see the output image has just bigger dimensions than the, and we attend to every pixel as much as possible. So we use here, like now, we use the left top value of filter matrix multiplied by the right bottom value of our image. Okay, please move on. So the padding is full here. This is get and the stride value.
Try this one.
Yes, why?
Because we just move by 1.
Okay, okay, thank you. Now this, what is the stride? What is the padding?
So here is no padding, and stride is
2.
Is 2.
Yeah, the stride is 2 because we jump over just this row, over this column here. Great. The last example here, this one.
So padding is 1 and strike is 2 also.
Yes, and the default value of padding is like in default values. Is it same or is it full?
Neither. No.
Well, yeah, it's good that that's not easy for now. The padding is same now, but it can be non-obvious since the shape of the output matrix does not coincide with the shape of input matrix, right? The reason is that this stride now equals 2, right? And well, if we want to preserve the dimensions having this stride 2, we would have to apply a lot of padding, which is equal to half of the shape of our image. And that's not normal because we would have a lot of zero values, right? So why the padding is same here? Because if we would have the stride equal to 1, the shape of the output matrix would be 5 by 5, it would be okay. But since the stride is 2, it's okay that our image has just lower shape. And in fact, it has the shape equal to taking just sailing, I mean, just rounding into the bigger side, the input shape of matrix divided by the stride value. So 5 divided by 2 is 2.5, sailing, we get 3. So this is why the padding is same here. Okay, thank you. And there is also a backward type of operation called transposed convolution, which allows us, instead of decreasing the dimension of our image, it allows us to just vice versa increase the shape of image. Before we move up to it, let's see how the convolution operations are applied in neural networks. So a convolution is a linear operation. It just equal to a linear layer, but to apply it as a linear layer, we need to somehow reshape this convolution matrix. So here is the kernel, just our filter matrix. Yeah, it's sometimes called the kernel. It has shape 3 by 3, and we just compose a matrix from this very 3 by 3 to get the shape 4 by 16. Why this very form? It can be non-obvious for now, because we would also just underneath the neural networks, we would also reshape our input matrix. So this is the input matrix, and to apply the linear operation like convolution, to apply it as a linear transformation, we also need to flatten our matrix so that now it's presented as the input vector 16 by 1. Yeah. The next thing which we do is we calculate the shape of the output matrix. For instance, if we have the filter size 3 by 3, like we saw in our kernel, it will be applied here, here, and so on. So the output shape will be 2 by 2. The output shape also needs to be flattened in the beginning. So we have the input vector of shape 16 and the output vector of shape 4, right? So to compose we need the matrix of shape 4 by 16 to be able to make the multiplication. We compose such a matrix. Here is a brief explanation of how these values are obtained. I do not believe it's just easy to understand how it's composed looking at this picture. And if you want to deeply understand how all these values can be obtained, you need to just write down this very operation and see how each pixel of the output image depends on all the pixels from the kernel and all the pixels from the input image. Yeah, and if you write it down and see how it depends on each of them, you will see that that's just the exact form of the matrix, that just multiplying the input by this matrix is equal to applying convolution to it. Yeah, so we multiply the matrices, get the output, and then we reshape it into 2 by 2, and this is like the output picture. Yeah, so this is how the convolutions can be applied and how they are applied inside the neural networks. Okay, so now let's speak about one of the most important tasks in computer vision, segmentation, and we'll see why the transposed convolutions, which I've mentioned previously, are used here. So the segmentation can be binary or multi-class. binary looks like this. So we have some objects, probably animals or zebras or horses, right? And we need to only segment this very part on the image. For instance, like this, having black pixels, like values equal to 0 for all the other parts and white equal to 255 for the target values. For instance, here, our classifier did not notice the second zebra in the image, right? Multi-class segmentation task is does the same, except for that we have several classes. Yes, 5-legged zebra we get. Funny. And for multi-class segmentation task, we need to highlight all the classes with different colors. For instance, the road with the purple, the cars with the blue, the people with red, and so on. Because, well, when our auto car from Tesla or Yandex is driving, it needs to treat the objects in the road differently. For instance, it's better to hit the other car than hit a person, right? So here are some video demonstrations how the segmentation works. And when we apply this to video, or like in auto cars, when we apply this in real world, what is done is the picture is taken each 5-10 milliseconds, and on each second we do this very segmentation task to detect all the objects presented in the image. Here is the demonstration for auto cars. Okay, so let's briefly answer some questions here. First of all, for such a task, what is the input for the network? What is the output?
So the input is like photos which are taken for 5 milliseconds, and the output are like multi-classes of different types of elements in the photo.
Yes, but what's the shape, okay, of the output for one image? Okay, so thank you. The shape of the output is just n multiplied by m. And if we want to highlight additionally, we can also preserve the number of channels. So what we need to output here for this image taken, well, the image is not this is the result of segmentation. The image is the photo of the road, right? We need to have the same number of height pixels, of width pixels, but we generally do not need the number of channels dimension. For instance, here we can use the black and white, just one channel way of representing the data to highlight different classes, right? So this is what is the output. The output is just the image, and it's either colored or not. It depends on the task and on how we want to represent it. Okay, the next question is, what's the activation function loss for a binary segmentation?
Softmax, maybe?
For a binary?
Oh, no, not for the binary.
Okay, so for binary classification, we have the sigmoid activation function in the end, so that we can treat the result as the probability of belonging to the positive class. And we have the log loss function as the loss function, which is specially invented for binary classification. For multi-class segmentation, just that's the same as in classic machine learning for binary class, for binary tasks, sigmoid and log loss. For multi-class tasks, softmax and cross entropy, right? And a question for some very clever guys, for a multi-label segmentation task, what's the activation function and loss? When several labels can be inherent to each object. You can use your voice to answer, yes, but well, in fact, that's not softmax. And I've heard this question on several interviews, and the correct answer is sigmoid and log loss again as the function. So multi-label is closer to binary classification. Yeah, it just has the same activation function and loss in comparison to the multi-class classification. And I hope that later in our course, we'll have time to see why exactly these function and losses. Okay, so about 10 or 15 more time of your attention. How the segmentation task is done. We have the input image like this. It consists of just height is the number of pixels in this side, width in this side, and 3 input channels, right? We need to apply several like 5, 10, 15, or probably 20 convolution layers to it to extract the features. And then we need it to reshape back, or probably like this, we do not need the input channels. We need only one channel to differentiate different objects in the image. Yeah, but let's recall the number of parameters in convolution layers. We have the, let's get back to our Stanford course. Here we have, here. The number of parameters is filter size by filter size multiplied by number of input channels plus 1 multiplied by output channels, right? And well, looking at this, we will see, okay, so we have like 16 channels as an intermediate value, for instance, 3, 3, 3, like totally 160 parameters, and it's not too much for neural networks, right? Well, that's true, but in fact, we saw how the convolution operation, how the convolution kernels are decomposed into matrices, like here, right? And we had 3 by 3 here, which was decomposed into 4 by 16, and 16, this was the shape of the original image, like here, 4 by 4, right? And imagine that instead of 4 by 4, like for image with such a resolution, we have about, I deem 64 pixels as a height and 128 as the width. So here we would have 64 by 128, and it equals too much, about 8,192, right? And here we would also have a much bigger value, and totally the number of just parameters in such a matrix, not learnable parameters, but just the number of values totally in the matrix, will be several dozens of millions, and we just applying this operation would last the eternity, and since we need to apply it 5, 10 times, just our networks will work very long. And that's not great. Moreover, for reasonable values of our just computer memory, such a large network will not have enough memory, and it will just end up with a mistake, with an error. Yeah, so the solution is as follows. We need to use the downsampling and our upsampling inside the network. So first of all, we need to decompose our input into low resolution, like here, where, for instance, the number of pixels across both dimensions is shrinked 4 times, right? And then we need to upsample it back to high resolutions. And this is the example of such an architecture, and you can see that several convolution plus batch norm plus ReLU plus dropout usually are stacked, and then the pooling layer is applied. So 2 convolutional layers, 1 pooling layers, and this is exactly pooling layers, which makes the decomposition. Just using again this stride of 2, we decompose the image across each dimension twice, right? So this is how these layers are applied in the network, like convolution, convolution, pooling, which decomposes again. And here we need to upsample it back. It's done in reverse order. So first the pooling upsampling, and then the convolution upsampling. But we saw how to do the downsampling, but how to do the upsampling from this resolution back to the original shape. This is option 1, not 2. Here we can see 3 options. First, these are the most primitive ones, but well, okay, max unpooling is applied in networks, and it's okay that it's primitive. The first is nearest neighbor. We need to get the 4x4 matrix from 2x2. What we'll do, we'll divide it into sectors 2x2, and for each we'll fill with the corresponding value, as you can see here. The next one is bed of nails, and instead of filling with all these values, we fill them with zeros. So one value is taken and all the other zeros. But it's obvious that both these methods lose a lot of information, add some noise, and generally they are not so good. So max unpooling is applied sometimes, and it's the modification of bed of nails. So we do the following procedure like here, but instead of taking only the predefined value, like here, the left top corner of a box, we fill with the non-zero value, the one which was taken during pooling. So here, this value was taken as the max one, right? So we decomposed it, some blah, 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 and then when we upsample it back, we go back here, see, okay, this very value was the maximum one. So we will fill this very value with the non-zero value. The same as here, the same as here, right? So here we will have the maximum, we'll fill it here, and so on, and all the other will be zeros. That's the max unpooling. And now the transposed convolutions, which can just transform our input back to its original dimension. Just restore the dimension of it. If previously we used to multiply the matrix of shape 4/16 by vector of shape 16 to get the vector of shape 4, now we'll do the reverse operation. We'll multiply the transposed matrix like 16/4 by our input 4/1 to get the output 16/1, right? So if the input image is of shape 2/2, the output will be of shape 4/4 in this case. And this is how the transposed convolutions works. So if you look at this picture, you'll see that it's of no difference with simple convolutions. Like it's the same as taking the convolution with padding value equal to 2 here. Yeah, there are, or probably, yeah, it's the full padding here, and no strides. It's the same. But just as we do the upsampling now, the hyperparameters are referred to slightly differently. For instance, since if we treat it as a transposed convolution, then the padding equals to 0, since this is the normal value for padding for transposed convolution. And in transposed convolutions, the padding, if just for conventional convolutions, we use padding to increase the dimensions of the output image. Here we use padding to decrease the number of the output shape, and no padding would refer to as taking just the square 3/3 to be able to apply our filters, and that's all. So the more padding we add, the less is the shape of the output matrix. That's the transposed convolutions. So this is just we've seen it just now, and this is how stride is applied in transposed convolutions. So when we want to apply the stride, instead of moving our filter matrix by several pixels, right, we just add 0 rows and 0 rows and 0 columns to our input image, so that this is referred to as stride in transposed convolutions to increase the output shape of the matrix and probably get some different representations of a data. To better understand the transposed convolution, I hope we'll have enough time on our next class to see that it refers to as just taking each value of our matrix and multiplying it by the filter matrix. So we have some filter matrix. It's multiplied by this value, and this 3 by 3 square is composed of the result. We multiply it by this value, and this 3 by 3 value adding up for these 3 elements is just this the right top square. Yeah, so that's easy. We just multiply each value by a filter and sum it up, but we'll see it later how it works. And yes, for padding, for instance, on this picture, in this picture, the transposed convolution has no padding. I'm sorry, has full padding. Yeah, full padding in transposed convolutions means adding no padding, right? So it's the game of words. Like when we have padding full, we have just the output shape is as small as possible. There it is. Okay, so that's I wanted to speak about. As for the layers, yes, here we can also see some similarity, some loss functions to measure the similarity of 2 target matrices, and you can see that all of them use the intersection of 2 just images. Like we have some correct boundary boxes and we have some predicted boundary boxes, and to measure the similarity, we calculate the number of intersected pixels in just in 2 targets. There it is. So for our next class, what we'll do, first of all, we'll deepen into this notebook. That's the example from Torch, and the CIFAR 10 data set is used. It's one of the most popular data sets in computer visions. It consists of 10 classes, and yeah, we'll deepen into it to see how it just works. For now, we can see some interesting things, like here is our model, and here we, as we've described, convolution, activation, pooling, convolution, activation, pooling. It may be non-obvious why we use the same pooling here and here. Well, because pooling has no parameters, and if we use conv1 and conv1 here, then this will have different shape comparing to the current variant, right? And pooling, it has no parameters, so we can use it the same as activation function. Just we need to predefine the kernel size, the stride, and then apply. Then here the feature extraction part is over. We flatten our input, and then we use the linear layer, just dense layer activation, dense layer activation, and the last dense layer. There it is. The same cross entropy loss, since we have the multi-class classification task, as GD or probably Adam could be used. We train our model for 2 epochs. Here is the loss. We see it diminishes gradually, right? And here is the example of predictions of a network. Here are 4 images. Here is the cat ID, right? The ship, and the plane. And the predictions are car, truck, car, plane. Cat, cat, truck, car, plane. So 50% of them are correct, other 50 are not correct. And what's interesting, when we output the accuracy for each class, it says the accuracy for ship is the best one, though we saw here that for 2 ships, it has, our network has mistaken. Okay, so yeah, next time we deepen into this, then we see how the autoencoders work. In week 4 of your Coursera course, they'll speak about autoencoders in view of classification of computer vision tasks, but in fact, autoencoders are very popular in another field of machine learning, recommended systems. They are most of them are state-of-the-art methods. And since we are having an intro to deep learning course here, and we want to get you acquainted with all the fields of machine learning, we'll deepen into recommended systems as well for just half of the class, and see how autoencoders are applied to can be applied in recommendation system tasks. Yeah, if we have some time, we'll speak about the tracing or tracking method. We still don't know how to correctly pronounce it. It's a state-of-the-art method for detecting the outliers and measuring the influence of training data onto the test data. If we do not have enough time, we'll postpone it for our seminar number 5. Okay, so in case there are any questions, we have time now. Feel free to ask them.
So,
Mhm.
sorry.
Yeah.
Can I ask, about deletion? So, what is like the deletion size? If it's, for example, not 2 but 3, it's the size between like between.
Between what? Yeah, that's the question, right?
Okay.
It's the size of input pixels between each 2 consecutive values of boxes onto which we divide our image. So, for instance, here is the deletion 2, and let's imagine we have deletion 3. So these the shadowed values are the values of our filter matrix, which is 3 by 3, right? And the top left value will be obtained by multiplying these just input, this filter matrix by the following values. This one, then the relation is 3, so we move by 3 pixels down, 1, 2, 3. This is the second value, and this 1, 2, 3, the third value. This is the first row. Then across the width, 1, this one 2, 1, 2, 3, this is the third. And so for this very example, when applying deletion equal to 3, the output will be just one value, and it will be the result. You see.
Okay.
Okay, so any other questions? All right, if not, thanks anyone. Yes, next time we're meeting on Saturday, I hope offline, in case no other COVID accidents take place. And yeah, next time we will not have any tests, but we'll have them on seminars 5 and 6. Okay, so
the next
thanks
seminar
everyone.
on Saturday. The next seminar on Saturday.
Yeah, next Saturday, not this one.
Next Saturday. Okay, not this one. Okay, thank you.
Yeah, thank you. Bye-bye.